Simpson's rule and the prime counting function. My motto: plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. The first part of this presentation is necessary for all that follows, so don't be put off or bored by it. We know from our calculus lessons that the integral of the reciprocal 1 over x is a natural logarithm, and I remember way back in the late 70s an Open University program giving the value for it between the limits 1 and 2, but I couldn't remember what it was. So for the first time in the 12 years or so that I have owned my Casio FX 570W calculator, I used the integral function on it to find out, and surprisingly simple it turned out to be too. The handbook tells you that the integration is carried out using Simpson's rule, and that is all I am going to say about Simpson's rule, but not the inputs and outputs for the integral. Pressing the integral button displays the integral sign and the opening bracket. One then enters the expression to be integrated using the alpha x register, as other alpha registers are invalid. This is followed by the data separator, then first limit, data separator, second limit, data separator, and then a value from 1 to 9 which controls the number of valid digits of the approximation of the integral, but can be left blank, followed by the closing bracket. The result that was returned was the natural logarithm of 2 equals 0.69314718, so my question was answered. Further trials showed that the answer was always the natural log of the second limit divided by the first limit, and as would be expected in hindsight, if the first limit was bigger than the second, then the result was the same but negative. So to integrate the reciprocal, don't use Simpson's rule or any other method. Just divide the second limit by the first and convert to natural logs. Job done. Incidentally, you could use Simpson's rule to generate a table of logarithms, natural or to base 10, should you be inclined to do so. Having watched 5 or 6 presentations of the Riemann hypothesis, roughly 6 hours in all, and all of which agreed with each other in general, but not always in the detail, I realized that what I have demonstrated was highly illuminating. The Riemann hypothesis presentations start with the discovery by Carl Friedrich Gauss as a 15-year-old schoolboy that there was a connection between the primes and natural logarithms. This, coupled with the fact that mathematicians have set their stall out to find a way to enable them to estimate the number of primes up to any given number n, has become known as the prime counting function, denoted πx and shown in the above graph. Zooming out to ever greater values results in the waviness of the curve being smoothed out, as shown in the 2 graphs below. Gauss also generated 2 approximations for the prime counting function, and these are plotted, one above and one below the curve. It was conjectured that the ratios of the 3 would converge to 1, and which, having now been proved, has become known as the prime number theorem. For more on the predicting equations, you will need to look them up on Wikipedia or in the Riemann hypothesis videos on YouTube. In order to facilitate the estimation of the number of primes up to any given number, it is of course necessary to get practical measures as a starting point, and the results are shown in the attached table. The total number of primes in a number field of size 10 to the power n are given in columns C and B of the table. The chance of a number being prime is column B divided by column C, and is given in column D. Subtracting adjacent values, small from large, in column D gives the values in column E, and as we go down column E we see that the results approximate more and more to the natural logarithm of 10, which was what Gauss observed, but on far smaller samples. For the predicted equations for the prime counting function that have been generated by the mathematicians, you will need to look them up on Wikipedia or look at the Riemann Hypothesis videos on YouTube. The above graph shows the reciprocal function of the area beneath the curve, which for limits of 1 and 10 is the natural log of 10 divided by 1, as per Simpson's rule. This can be obtained with the red vertical limit lines shown below the curve, which includes those of the primes, as follows: natural log of 2 divided by 1 plus the natural log of 3 divided by 2 plus the natural log of 5 divided by 3 plus the natural log of 7 divided by 5 plus the natural log of 10 divided by 7 is equal to 2.302585, the natural log of 10, denoted ln 10, which you can confirm on a calculator. Also, we can now see that areas under the curve between 10 to the power 1, 10 to the power 2 and 10 to the power 2, 10 to the power 3 and 10 to the power 3, 10 to the power 4 and 10 to the power 4, 10 to the power 5 and 10 to the power 5, 10 to the power 6 and 10 to the power 6, 10 to the power 7 and so on and so forth ad infinitum are all equal to the natural log of 10 equals 2.30258, since 10 to the power 2 divided by 10 to the power 1 is equal to 10 to the power 3 divided by 10 to the power 2 is equal to 10 to the power 4 divided by 10 to the power 3 is equal to 10 to the power 5 divided by 10 to the power 4 is equal to 10 to the power 6 divided by 10 to the power 5 is equal to 10 to the power 7 divided by 10 to the power 6 equals 10, for all and so on and so forth ad infinitum. This I confirmed on the Casio FX570W for the limits 10 to the power 96 and 10 to the power 97, being the largest exponents possible without exceeding the calculator's limits. Hence the reason for the appearance of 2.30xx, an approximation to the natural log of 10 equals 2.3025 in column E of the table on slide 5. Furthermore, the prime counting function plots upside down as shown in black on top of the reciprocal curve, a perfect fit. Who'd have thought it? It is obvious to any rational thinking person that the emergence of the natural logarithm of 10 when sieving the primes has absolutely nothing at all to do with any mysterious, unknown or almost surreal connections between them, but is due entirely to the logarithmic nature of the reciprocal function and the fact that the decline in the distribution of the primes is reciprocal. So when one reads or hears remarks such as was increasing by 2.3 rather than 1 every time Gauss multiplied by 10 is because primes favour logarithms based not on powers of 10 but, or, provided the first real support of some connection between logarithms and primes, or discovery of a connection between primes and the logarithmic function, just treat it all as baloney. Looking at the data from slide 5, one can see that each increase in the number field as powers of 10 includes the primes found in the preceding fields shown red, so the field size and prime number count were modified as shown by the data in blue in columns D and column E to exclude them. The chance of a number now being prime is D divided by E and is given in column F. Subtracting adjacent values, small from large, in F gives the values in column G, and as we go down column G we see that again the results approximate more and more to the natural log of 10 equals 2.3025 in a slightly more regular manner. The slide shows the plot of the chance of a number being prime for increasing corrected batch sizes, and we see, surprisingly in view of what the mathematicians have derived, that it is a common garden straight line plot, with almost perfect correlation. We will see on the next slide that the differences between the data points in column G of the table plot as a reciprocally decreasing curve. Since differences between equally spaced points on a line are always equal for perfect straight lines, it tells us that what appears to be a straight line on the scale of the plot and to the regression analysis will, if extended, always be slightly curved. I reckon this is the first and one and only factual demonstration of an infinitely long pseudo straight line, the reason for whose finitely small curvature we know. The table shows just how small the percentage error is between the actual and the estimated quantities of primes, and successfully satisfies the criteria for counting the primes up to any number n with reasonable accuracy. We do, however, need to keep a running total of all the previous determinations for a gross count. It is inevitable that the count will drift away from the real value for the quantity of primes, but it is beyond our reach to check it out, so is of little consequence and does not affect our understanding in the slightest. So the analysis of the corrected data tells me that what I have shown is all one needs to fully understand how the primes increase with increasing magnitude, despite the relatively minor inevitable variations in the actual quantities of the primes. As an example of what I hope to show is an analogy for the Riemann hypothesis are the two numerical expressions that give the same numerical output of 414. Expression 2 is just a complicated expression derived from 1, so achieves nothing. Likewise, I consider that the math magicians have emerged from the only door of the numbers laboratory, charged round the corridors and departments of the institution in which it is housed, landed back in the numbers laboratory without using the door, and then re-emerged through the door shouting, "Eureka! The Riemann hypothesis, the hardest problem in maths." As far as I can see, all that they are claiming for it was there when they first left the laboratory. After watching the YouTube videos, 1. I could appreciate the brilliance of the complex mathematics and the computation of 10 trillion zeros, which fell on the half line, but 2. All that seemed to be derived was a reconstitution of the staircase profile of the prime counting function graph, and 3. A Riemann spectrum that, after being subjected to a Fourier transform, produced a spectrum which revealed the primes but little else. Now, like it or lump it, the staircase was there without the need for the Riemann hypothesis, as was the spectrum, which can be generated from the staircase plot by only plotting the rises and making the prime rises 2 or 3 times the height of the composite ones, QED. So I fail to see or believe that anything constructive will ever result from a constructive proof, if one can ever be found, of the Riemann hypothesis. Thank you for watching the video.